All right, everybody, welcome back. We're almost there. There's only a few chapters left. There's only 8 sections left. I know there's 8 sections left because there's 8 hypothesis tests left. And we're doing 2 of them today. We're going to do 10.2, which is on one sample proportion test. And 10.3 is on one sample mean test. All of them have every test thing that we do from now on has 5 steps for everything from now on. Step 1. Well, these are the 5 steps of hypothesis testing. Step 1 is identify and label. H naught, the null hypothesis, and HA or H1, depending on what thing you're reading, the alternate hypothesis. H naught always has an equal sign. HA has less than, not equal to, or greater than in it. One of those. A couple of the final tests have sentences or phrases rather than equations, but like for the first 5 or 6, we have equations. Chapter 10, we're doing a one proportion test, and we're looking at a means test. So those are the things that we could fill in on the left side. For now. On the right side, we're going to have a number, and it needs to be the same value for both of them. StatCrunch will make sure you do it that way. This step 1 is the only step that changes depending on what type of test we're doing. But it always has H naught and HA. Step 2 and 3 are interchangeable. But both must be done before step 4. So it doesn't matter which one I label these two. We'll say it's find the test statistic and the p-value. And 3 is find alpha. Use 0.05 if none is given. Make sure everyone's done. Some people are still writing. All right, step 4. Step 4 is where we actually got to start doing some work. And it's simple work. Compare p-value and alpha. There's 2 possible outcomes. If p-value is less than alpha, then the p-val is too low. Reject the hoe. Support HA. I like calling this the verdict. This is where we make our decision. We pass judgment. We decide what we're going to do. Option B, p-value is not too low. It's greater than or equal to alpha. Verdict. The p-val is not too low. Do not reject the hoe. Do not reject H naught. Do not support HA. And our concluding sentence will have, there is not enough evidence to support HA. This is the knots. They go together. Step 5 is our concluding statement. It's always about HA. And you need to say what HA is in the sentence. You need to state HA in it. If you don't do it on the final, you're gonna lose a lot of points. If you just say there's enough evidence to support the claim or not support the claim, I don't know which claim you're talking about. I don't know if you know what you're talking about, so I'm not giving you credit. You need to state HA in it. Every example I do where we have a problem, I will do that myself. And it's based on our verdict above. So if we have case 1, p-value is less than alpha, we are supporting HA. If we're supporting it, it means there's enough evidence. There is a reason to support it. There is enough evidence or sufficient evidence to support the claim that, and then you should paraphrase HA here. Sometimes you can just flat out copy and paste. Literally, if the sentence is worded in such a manner that you can just word for word in the exact sequence it has it, grab it and put it in. You'll see that today. B is when p-value is greater than or equal to alpha. So we do not support HA. There is not enough evidence to support the claim that, and again, paraphrase HA here. So. And in 10.2, we're doing one proportion test. Proportion test for one sample. H naught will be P equals something. And HA is P does something else. Less than, not equal to, greater than that same value. We do need the data to be normally distributed. So either A, they tell us that it is, or B, we verify that it's normal enough by doing n times p times 1 minus p is greater than or equal to 10, and n is less than or greater than, nope, less than or equal to 5% of the population. If all that's true, we can deduce stats, proportion stats, one sample, just like confidence intervals. They are connected, and I'm going to show you today how they're connected, what this all means. You don't need it for the thing, but we will use mu equals p hat and sigma equals square root of p hat times 1 minus p hat over n for demonstration purposes only. You do not need to do this for most of the assignments. Give me a second. Okay. Ready for the first example? One more second. Give Angel a second. Thank you. All caught up? Yeah. Everybody else ready? Okay. So this is something, and this is, I did this in fall of 2021. It is believed that when I get that, less than 40% of students want to take statistics face to face. In a face to face setting. The following data was collected in fall of 2021. We recorded what type of class it was, whether it was Math 21 without support or Math 21 with support. Face to face. And 135 for without support. And 254s for with support. And the number of students that are registered for online classes in that same semester was 550 and 241. So if we do a little total column, this is 685. This is 495. This adds up to 1180. Let's see, this is 389 and 791. Test my claim at alpha equals 0.05. All right. So let's go through the 5 steps of the hypothesis test. I'm sure everybody's good. Everybody looks like they're done writing. So step 1, we need to identify H naught and HA. It says less than 40% of students. Where should I put that? Which one does that go into? That is H naught or HA? HA. Less than 40%, 0.40. This is a proportion. Because H naught is always the equal sign. So usually they won't say the old information, but they're like, you can extrapolate it from what was being asked. So I'm using 0.40 as H naught. And this is students who want to take face-to-face. Step 2. Stat crunch time. Well, we can do alpha right now. Alpha is given as 0.05. Like I said, 2 and 3 can be done in any order. Now, step 3, they're going to want, for stat crunch, they're going to want X and N. X is the number of students that wanted to take face-to-face, 389. And N was the total number of students, which was 1,180. That's what we're going to use in stat crunch.
The 389 was the students who want to take face-to-face, right?
Who want to take face-to-face, yeah.
Gotcha. And I'm just paraphrasing, make sure I understand it.
Okay. Stat crunch, here we come. We're going to go stats, proportion stats, one sample with summary. The number of successes was 389. The number of observations was 1180. We'll come back and look at the confidence interval in a second. But we're doing R's, and P here was 0.40. And notice how HA updated all on its own. I didn't have to put that in. So this is the exact same method we did for confidence intervals. We're just not going to click on confidence intervals. We're going to leave hypothesis test selected. We just have to choose HA for what it is. We had P was less than. So make sure you choose HA and set H naught. I'm gonna click on optional p-value plot just to see what it has. I don't remember seeing that before, so that sounds kind of neat. Click compute. Our test statistic that we want to write down is this one. So my z-stat is negative 4.932. And my p-value is less than 0.0001. All right, let's finish our test. Step 4 is to compare p-value with alpha. I'm going to use 0.0001, but it says it was less than. Alpha was given as 0.05. Is p-value less than or greater than alpha? What? Less than. So the p-val's too low. Reject the HO. Support HA. That's my verdict. I'm supporting HA, and HA was that less than 40% of students want face-to-face stat classes. There is sufficient evidence to support the claim that I'm going to come up here and I'm actually just going to jack the sentence. Less than, this is flat out from the sentence, less than 40% of students want to take stats in a face-to-face class. And I'm going to add in versus online. I literally just hijacked the sentence of a book. Damn near word for word. I just changed the last, I add a little bit at the end. Okay. I want to show you guys how this compares to the confidence intervals. So to do the confidence interval, well, we can use the same stuff for the confidence interval, but I also want to show you it on the normal calculator. I want to tie this all in. Because we did a lot of shit with the normal calculator. I told you we want normal distribution. I want to show you why. All of this shit's going to tie together. So for the normal calculator, we need the hypothesis test is done. We need mu, which is P, which is going to be 389 over 1180. StatCrunch actually gave that to us. It says sample proportion is 0.329661. I'll do 5 decimal places. We also need standard deviation. So standard deviation for the proportion, square root of P times 1 minus P over N, square root of 0.32966 times 1 minus 0.32966, all over 1,180. If you put that in a calculator, you're going to get 0.01368 to 5 decimal places. We also need a little bit more to show how everything connects for the confidence interval. Because we need a confidence interval, or we need to tell what percent. So this what HA was, P was less than 0.40. That's a left arrow. This is a left-sided test, left-tailed test. For the one-tailed tests, our confidence interval, we're going to use 1 minus 2 times alpha. So 1 minus 2 times 0.05 is 0.90 or 90% CI. We're actually going to use this 0.90 in the normal calculator as well. In normal calculator as well. As the area for between. It's going to tie in our bell curve, our confidence interval, our normal calculator. You're going to see how it's all connected. And hopefully it'll actually like mean something. Because right now it feels kind of arbitrary to say p-value is less than alpha. Where the fuck did they get that? Who gives a fuck about that? What is this bullshit? Sounds kind of like made up. There's some fucking like, we're not showing you how the sausage is being made. I'm not going to show you like the mathematics behind finding p-value, but we're at least going to show the sausage being made. Like how this all works. Everyone ready? Whoops. All right. So if we want to do the normal calculator. I'm going to enter the mean we had, which was 0.32966. And I don't remember the standard 0.01368. I'm going to click on between and I'm going to say 90%, 0.90. And this gives me 0.3072 and 0.3522. Now, what does that mean? Let's go look at our confidence interval. We had 389 out of 1180. We had a confidence interval of 90. Look at that lower limit and that upper limit versus what's right here. They're the same thing. So the confidence interval is telling us what the boundaries are on the normal calculator. On doing a normal calculation, because we're saying it follows a normal distribution, so we're using a normal distribution. Look at it. 0.30715 rounds up to 0.3072. 0.35217 rounds up to 0.3522. So the confidence interval is pulling, it's doing all the normal calculator work for you. How does that tie into the hypothesis testing? Does the p-value plot show it? Well, kind of, not really. So I'm gonna do the rest by hand. Z-stat is like the number of distributions. Because remember, z-score is like number of distributions. Standard distributions, a number of standard deviations, not distributions, number of standard deviations away from the mean. This is saying that our score is 0.493 deviations away from the mean to the left. So we had both normal calculator and CI gave us these boundaries. It had .307 and 0.352. And this was our confidence interval. With our sample proportion right in the middle as 0.32966. That was our P. Where is 40% on this graph? Where is 40% on this number line?
Further to the right.
It's quite a bit further to the right, isn't it?
Yeah.
0.40 is way over here. This was our null hypothesis. And our null hypothesis is far outside the region we are confident in. Thus, we reject H naught. We reject it. One of these examples we'll do today, it is not outside of it. We won't reject it, and we'll take a look at the confidence interval and see what happens there. So the p-value had its own bell curve. This is what showed up on that when we clicked on the p-value plot. They had some shit like this. This was the p-value plot in StatCrunch. And our p-value, our proportion was way over here, way outside their accepted region. So let's say the p, even say it said less than 0.001. I'm going to say it was 0.0001. What this tells us is if the null hypothesis is correct, because we're rejecting it, but we don't know for sure if we're right, is true, then we're going to convert this to a fraction by shifting the decimal place to the right 4 times, and we get 1, and we add 4 zeros on bottom. This is the equivalent over as 1 in 10,000. Then about 1 sample in 10,000 will have an outcome like ours, as extreme as p equals 0.32966. Not very often, right? We do 10,000 samples, and only one of them is likely to have a proportion this low if 40% is correct. So that's also why we're rejecting it. This is what the p-value means. It's just too unlikely. It's not 5%, it's less than 1%. It's less than 0.1%. It's 0.01%. P-value as a decimal right here, or percentage right here, is 0.01%. That is less than what the alpha that we set. Alpha was set at 5%. We are far less than it. Let's take a 5-minute break. That will do 10.1 or 10.2. We'll do 10.3 in a bit. Hey, Mapper. All right, so question number one. Question number one says test the hypothesis. I'm not changed over, am I? Test the hypothesis that using the p-value approach, be sure to verify the requirements of the test. So they want us to make sure that n times p times 1 minus p is satisfied. Greater than 10 is satisfied. So if we do that in a calculator, 200 times 0.5 times 1 minus 0.5 should be 50. Is 50. 50 is greater than 10. So you're just plugging in n and p that's given above into this right here. It's been a little bit caustic of the last couple of days. I think you could strip the paint off the wall with what I've been doing.
Oh, man,
You're in the blast zone, Johnny.
that's all right. My dad was the same damn way. It's cool.
Then it says use technology to find the p-value. Then we're gonna go stats, proportion stats, one sample with summary. X is the number of successes. That's 105. N is 200. And we're doing the hypothesis test. P equals 0.5. HA is P is greater than 0.5. And we click compute and we get our p-value is 0.2398 to 3 decimal places, 0.240. All right, so let's come over here and talk about this on camera over here. So 10.2, number 1, we have H naught, P equals 0.5, H1, P is greater than 0.5.
Is H1 the same thing as HA?
Yeah, H1 is the same as HA. Some books do H1, some do HA. Like the idea is looks like a 0 and a 1, and they do 0 and 1. And I think the O is really supposed to be a 0.
Okay.
But that's like confusing. They should call it HN and HA. So like null hypothesis and alternate hypothesis, because that's their names. They have names. They, for some reason, use like weird subscripts that don't apply. They do. H naught is universal. That's the null. And they gave us n equals 200, x equals 105, and alpha equals 0.05. Now, before I continue, I want to show how this looks. Our confidence interval, I would use 1 minus, since it's greater than, this is a right-tailed test. I'm going to do, it's 1 minus 2 alpha. When it's not equals, we just do 1 minus alpha. But for the one-tailed test, we do 1 minus 2 alpha. again, we get our 90%. I'm gonna go grab the boundaries for this. So for this, we get a lower limit of 0.4669, which is like 46.7%. And we get an upper limit of 0.5831, which is like 58.3%. And it says our proportion, our p hat is 0.525. So that's what's in the middle here. Our p hat is 0.525 or 52.5%. Over here, we've got 46.7%. And over here, we've got 58.3%. This is our confidence interval. Where does the null hypothesis land in this? It's in the middle, right? It's between, somewhere between 46.7 and 52.5. That's where H naught P equals 0.5 is. So the confidence interval is showing us we shouldn't reject H naught because it's possible. Because it's a viable outcome. That's what the confidence interval is telling us. Our p-value that we got, p-value said 0.240. When we compare that with alpha, the p-value is larger. So our verdict would be do not reject H naught. Do not support HA. So the next question it asks us is to fill in the blank. We're going to say reject the null hypothesis. Because the p-value is greater than alpha. I'm going to slop on a little bit more about that p-value. We have p-value is 0.240, which is like 24%. Or 24 out of 100 samples will have a p-hat as high or higher than ours. Because we are above it. So we're saying that there's a 24% chance. Let's see, does it have a good? No. Let me do the hypothesis jet value plot. There we go. Look at this p-value plot. Oh, I gotta wait till you're done writing.
Can you move your clicker down just a little bit, Dave, so I can get the rest of the green? Thank you.
There's a lot more you gotta get if you were on the green.
No, let me bring it up first because.
So we do reject the.
No, we're not.
We're not rejecting, that we reject the null.
They're the same. We're not rejecting H naught. We're not rejecting the null.
It says do not reject HO, and then it says reject.
Oh. Yeah, I fucking said that wrong. Do not reject.
Okay.
Thank you. I fucking said that completely wrong.
You did initially have it.
I verbally said it,
Thank you.
but then I like wrote something different. We're not gonna reject the null hypothesis because p-value is greater than alpha. You ready, Johnny?
Yeah, I'm just writing that little part you said was very good. Go ahead.
Alright. So this is what I was trying to say. Our p-value here is right here on the, like, if p is 0.5, then us getting a 0.525, there's a 24% chance that we'll have a result that's in this red region. So as extreme or higher. If we're on the low side, I would say as extreme or lower. As low as our value or lower. Here it was above it. We were doing a right-tailed test. So the right-tailed test kind of indicates the higher part. Generally, when we're looking at lower, it's going to be less than over here. I'll say P is less than. And that's when we'll have lower. We are not rejecting the null hypothesis because the p-value is greater than alpha. Next question. So you got to see it both ways and why. Like the p-value or like the proportion value will either fall in the confidence interval or it won't. If it falls in the confidence interval like it did here, we don't reject it because we're confident that it's part of the region. But if it's outside of it, like it was in the last problem, then we reject it because it's outside of the region we're confident in. The p-value, that's what's really happening. The p-value is a shortcut, a fast method to get the same result. You don't have to stop and plot everything. You don't have to draw the graph. You just go, is p-value less than alpha? Boom, headshot. You're done. Okay, that's how p-value P-value is beautiful. Question 4, some have argued that throwing darts at the stock pages to decide which companies to invest in could be a successful stock picking strategy. Suppose a researcher decides to test the theory and randomly chooses 200 companies to invest in. After 1 year, 106 of the companies were considered winners. That is, they outperformed other companies in the same investment class. To assess whether the dart picking strategy results in a majority of winners, the researcher tests. You're not even looking at the same screen I am. The researcher tests H naught is P equals 0.5 versus the alternate P is greater than 0.5. And they told us what they got. We could go verify this on StatCrunch. We're just going to take for granted that what they said is correct. So they got 0.1981 as our p-value. Explain what this p-value means and write a conclusion for the researcher. So question number 4. This is dart tossing for stocks. Stock picks. That's just a quick, a summary of what the paragraph says. They had 106 out of 200 winning dart throws. Like they paid out well. They said H naught was P equals 0.5. HA or H1 as they called it, P was greater than 0.5. They wanted better than 50%. The p-value they got was 0.1981. The alpha they want us to use is 0.1. They didn't tell us it followed the normal distribution, but I'm sure we could check it. Or just flat out assume that tossing darts does it, but I don't know that that's a safe assumption. But if we do n times p times 1 minus p, we use n equals 200, we're still above that 10. Here, p-value, they want us to make a verdict. Our p-value is greater than alpha. So it's not too low. Do not reject H naught. Do not support HA. If we're not supporting it, there's not enough evidence. There is not enough evidence to support throwing darts for stock picking. As a winning strategy. I want to note it, if you do 106 over 200, that's 53%. So 53% is above half. Like they actually were better than 50%. But that's just one sample. We can't rule out 50% as, or under 50%. Based on the p-value. If we did the confidence interval, we would see that 50% lies within. And so do lower values. So like, even though we had 53%, it still could be 50%. We might just have had some really lucky throws. The way they've worded their thing, they ask if we're rejecting H naught or not. And so we're gonna say, because the p-value is large, we reject the null hypothesis, or we do not reject the null hypothesis. You guys kind of see how these hypothesis tests work? We go through them, we make a verdict based on the p-value. We list what H naught and HA are, but we make a statement about HA. This is gonna carry over to 10.3, which we're gonna start right now. As soon as everybody looks like they're done writing this. And everybody does look like they're done. So 10.3 is doing a one mean. 10.3 is doing a hypothesis test for one sample for means. I like to call this the one mu test. That like says it succinctly. Your information is H naught is mu equals something, and HA is mu doesn't. It's either not equal to, it's less than, or it's greater than. All the same ideas with the p-value and the confidence interval, and using the normal calculator, translate over to this. So I'm not gonna do all that work again to show it to you. We're just gonna go with stats, t-stats, one sample. We've got with data and with summary. I'm gonna do an example with summary today. On Tuesday, in the Math 321 class, I'm gonna do an example with data. So when Tuesday rolls around, and after that, you can watch it if you're still doing the homework for this section. You can see a video with it, but it's really, I'll point it out like when we're rolling through it on StatCrunch, when I have it back up on the screen. Having data just means less work. You don't have to enter anything in. Like here, we actually have to enter in shit. Like we had to enter in X and N. If we had the data, we just say, go to that column. Just look at that column, do all the work, StatCrunch. It'll do all the work. We do, like, just like we wanted some requirements met for proportion. Now we want a normally distributed population. So you want to look for box plot has no outliers. It was a simple random sample. You want it to be random. And all the things are independent. We will actually have a hypothesis test where dependency is required. There has to be dependency between two different groups. It's called a paired test. And you want n greater than or equal to 30. I'm gonna put an example in for a second, in a second. I have something for your entertainment. It won't take but a second. The following is assuming you watch Star Wars. If you do not recognize the scene on bottom, the next joke will tell it. Explain it. I'm having trouble with this riddle. How are children like tattoos? They're both permanent. Obi-Wan says, and Anakin, Lord Vader, says both can be removed with lasers. That scene on the other one is when Anakin goes full Sith Lord, goes into the Jedi temple and kills all the Jedi children. That would be so much fucking fun to do as a virtual reality game. Just go in and slaughter children with a lightsaber. Don't tell me children haven't pissed you off in your life and you're like, I really wish I could just beat the shit out of you. You know, sucker punch you, something. Choke you. Every child pisses off somebody. This is a way of doing it without regret. I know they're not going to put that in there, but it would sure be great. All right, so this is from our lecture notes that I have online, that file. In the 10.3 section, COS students read that Energizer batteries last at least 75 hours when used in a simple LED flashlight. They tested 25 AA batteries. I'm assuming Energizer. They found X naught to be, not X naught, X bar was 76.6 hours with a standard deviation of 4.43 hours. Test Energizer's claim at alpha equals 0.05. Here are 5 steps. Step 1. What is H naught and what is HA? Feel bad for students that write fast in here. Cause I see them. Y'all look up at me, you're like, you grab your phone, you're like bored. But I can't just like rush through and ignore half the class that's slower than you. It does give you time to quickly check messages or play with your watch, Fitbit. It says at least 75 hours. What does that mean in mathematics?
Less than or equal to,
Good guess.
that's the other one.
It's the other one.
Yeah.
It's greater than or equal to. At least means greater than or equal to, but we're gonna just say greater than. We're gonna say greater than 75 hours. And they have a sample mean, we're talking about mu here. So H naught is gonna be mu equals 75 hours. I'm gonna need my test stat. I need my p-value. And I need alpha. I have alpha already, it's 0.05. StatCrunch is gonna want the information we have. They're gonna want X bar, S, and N, which we're all given. 76.6, 4.43, and 25. You guys ready? So here we're gonna do t-stats. One sample. I'm gonna show you what the width data looks like real quick. All it does is it wants us to select a column and do the hypothesis test. We don't have that though. We have a summary. So we're gonna do with summary. And so we have to actually enter in the results. 76.6, 4.43, and sample size is 25. Mu was 75, and HA mu is greater than 75. I'll throw in the p-value plot, see what it looks like. Click compute. And it gives me a test stat. It says t-stat is 1.81. And my p-value is 0.0417. Let's look at what their graph looks like. So 0.0417 looks like it's almost up to 2 deviations. 1.80 would be 2 deviations. Or if t-stat was 2, it'd be 2 deviations. We're really close to that borderline, aren't we? We have our information. We come up with a verdict. Let's compare. P-value is 0.0417. 0.05 is alpha. P-value is less than alpha. What? Why are you shaking your head now? Yeah, we're gonna reject it. P-val is too low, reject the hoe. Support HA. All right, so for you good religious people, my favorite Latter-day Saint over here, if you do not like reject the hoe, you can say P-val is too low, the null must go. If you don't want to talk about hoes. I don't know what you have against farming equipment,
Listen and eat.
but if you want to say the null must go, there's still a jingle for it. Yeah. Or so the p-val is too low. The null must go. Get out. You're rejected. You don't like reject the hoe. That hurts. It just hurts. You're not even an old lady. I expect old ladies to not like that sentence. I don't know why it's gotta be a lady. I don't think guys and old guys give a fuck. I'm using myself as an example because I'm an old guy. All right, so we're rejecting it. We're supporting HA. HA was that they last at least 75 hours. And so there is sufficient evidence to support the claim that Energizer batteries, I'm going to say AA batteries to be specific, last at least 75 hours. When used in a simple LED flashlight. I literally hijacked the sentence up here. You don't got to be creative. You can literally usually copy down verbatim what it says. Unless they've got some weird wording. Every once in a while it's weirded word. Worded weird. Weirded word. That don't even make no sense. I got one final topic I want to address to you in this section. And it's about statistical significance versus practical significance. When p-value is less than alpha, we reject H naught. That's just the rule. We reject the null hypothesis. If n is really large. Oh, first off, we say that's statistically significant. If we reject H naught, it's statistically significant. If n is really large, then sigma has divide square root with an n on bottom. it can make sigma really low. And it will cause us to reject values. We may reject values. Let's put this. We may reject values that are normally close, that are not too far. This is also from the lecture notes. A quick example, in 2003, the average age of mother at childbirth or first childbirth at their first childbirth was 25.2 years. Researchers believed it was higher. They use n equals 1200. And they found a sample age of 25.5 with a standard deviation of 4.8. We're going to test their claim at alpha equals 0.05. H naught is mu equals 25.2. HA, they say it's higher, it's increased. Mu is greater than 25.2. We're going to look at the results here. You guys ready? John?
Write down the HO, the mu and 25.2 and the other one real quick.
I've got it set up two ways. They've got a really large sample size with 1200. I've got it with 1200. I've also got it set with sample size of 100. Let's look at the 1200 one first. The 1200 one, they get a p-value of 0.002, which is below alpha, so we're going to reject H naught. And the curve looks like this. We're way out here. If we had just used a different sample size and got the same information, we would have had a p-value of 0.2033. So 0.002 for 1200, 0.2033 for 100. 0.203, we wouldn't reject H naught. So by having N really large, we've actually said it's statistically significant. So with N equals 1200, p-value was 0.002, and we reject H naught. When N equals 100, the p-value was 0.203, and we do not reject H naught. That's the only difference. By having a large N, the large N is making it statistically significant. But it's not practical. It's not of practical significance. I use 25.6, but it's not going to change. Doesn't change much. Actually, it changes the p-value a lot. If I actually use 25.5, this gets even lower. No, not as low. This one, correction. This is 0.0153. It's still a reject. This is 267, which is even a bigger reject.
If you're using what?
I had 25.6 in, and their correct value was 25.5.
Oh, just like a 0.5, it'll change it.
You going from 0.6 to 0.5 changed these quite a bit. The real issue, though, is this N thing. Here we reject it because N is large. Here we don't because N is not that large. Look at the actual ages, though. 25.2 years versus 25.5. Can you tell the difference between someone that is 25 years old in like 3 months and 25 years old and maybe 5 months? No, there's no practical significance to this whatsoever. But since N was large enough, it says it's statistically significant. So that's something to keep in mind, that while it may show significance, it sometimes really isn't in the big picture. With that, it's 7 o'clock. Get the fuck out. Have a good night. Have a good weekend. As a reminder, I'll be at Starbucks in front of Taco Joe's on Sunday from 8 to 10. If anybody's coming. Over in Visalia. Caldwell and Denver.
I'll be there, for sure.